right, here we go. Lots of stuff today. One of the things that you are going to see from your reading, and you've started the reading and you'll kind of continue that today, is that your book is going to take you through a bunch of different kind of examples of various things. What I'm going to do is I'm going to take you through kind of one reaction, and I'm going to take you through a whole wide variety of things, manipulations of that today. But I'm going to try to do it with some continuity by sticking with the same reaction. Now, the first comment that I have, sorry, I have to be plugged in because my battery is dying. And the reaction that you find is at the top of this handout right here. So this is the reaction that we're going to be focusing on today. That's the only reaction we're going to focus on today, is the decomposition of ammonium chloride into ammonia and hydrogen chloride gas. So what I have here at the first part of the sheet are just some pieces of information we need. The first is delta H. And this first delta H is done by using the heat of formation table and doing products minus reactants. That's what that is. Now, I do want to make a comment to you, and I know there's one in your chapter, and there's also one in the appendix that, I'll just open up the appendix. I know appendix 1 has a thermodynamic data chart, and in that chart, it lists heat of formation values for various ions and elements and things. But it also lists entropy values, S, which are given in kilojoules per Kelvin, because remember, entropy is very dependent on temperature, and it's really how much energy does it take to get that back to order. And there's also in here a delta G of formation values as well. And so you can find, we talked about delta G yesterday very generically, but you can find delta G values, and just like the heat of formation, like some of the products minus some of the reactants, you can do the very same thing with delta G values to find delta G. And so that's what I have on this handout. So this first one, you already are familiar with taking the sum of the products minus the sum of the reactants. And so we get this value, positive 176 kilojoules. What does that tell you about this reaction? Which one is it? Endothermic. So this is an endothermic reaction. Okay. The delta S that's listed here, this one was using that table that I'm alluding to. And again, just taking the products, ammonia and HCl, and subtracting the reactants, the ammonium chloride, just looking up those values. And when you do, you get this value of 284.5 joules per Kelvin, and then I converted it into kilojoules per Kelvin. What does this value tell you? It's a positive value. What does that mean? This is not G. This is S. Entropy is increasing. Entropy is increasing. So, ooh, Mike, there's a handout right there. Yep.
I missed the wrap.
There was no wrap. Entropy is increasing. So is it getting more ordered or more disordered? Disordered. You don't like it over there anymore? Oh, Boo is in his seat. Okay. All right, moving on. Delta G. I computed this. Right now, notice up at the top of the page, we're going to focus this first example at 25 degrees Celsius. So plugging in 25 degrees Celsius with our delta G is equal to delta H minus T delta S, and solving for that gives us a delta G value of positive 91 kilojoules. What does that mean? It is not spontaneous, right? So that's one way to find delta G. Another way to find delta G, because there's two different ones here, is to use the table in the book, the delta G of formations, and just like the, Hess's law thing, take the sum of the products minus the reactants and go ahead and compute it. And when you do, you notice you get the very same thing. Again, it is still not spontaneous. It's just it's an alternative way to find delta G. Now, what I do want you to notice is that each one of these has this little naught symbol throughout here. That naught symbol tells us that all of these values are being considered at standard states. Standard states means that if you're a solid, you're a pure solid. If you're a liquid, you're a pure liquid. That's fine. If you are a solution, your concentration is 1 molar. If you are a gas, your pressure is 1 atmosphere. And so as we kind of talk this through, we are going to be first considering standard states. And then we'll talk about what it means to be not at standard states anymore. Okay? All right, so the fact that this is positive 91 kilojoules, and we know, of course, that that means that, it's not spontaneous. What I want to do is to talk you through what does that actually mean. Because what it doesn't mean is that the reaction won't happen at all. It's very specific as to what it means, how that reaction will occur. So, a couple of interpretations. First is, if you put, I'm going to put R and P, reactants and products. So if you put the reactants and the products all together, in standard states, so in other words, I put some solid ammonium chloride, I put 1 atmosphere worth of hydrogen chloride gas, I put 1 atmosphere worth of ammonia, all in the same container. That's what I'm talking about. At 25 degrees, because that's our temperature of interest right now. The fact that it's non-spontaneous actually means that the reverse reaction is going to be favored to equilibrium. It's non-spontaneous. So that forward reaction isn't favored. In fact, it needs energy for that to happen. And so instead, it's going to actually go the other direction to get to equilibrium. Now, there's going to be a lot of things that I'm going to kind of tell you and interpretations I'm going to make. And stay with me. Because when we get through to the end, hopefully it will all become very clear to you. All right, another what does it mean kind of thing is if you put just the solid in a container at 25 degrees. So we don't put any gases. We just put ammonium chloride in a container. And here's what I want you to understand. A lot of times people will look at it and go, oh, it's not spontaneous. So if you put ammonium chloride in a container, nothing is going to happen. But that isn't true. It will still decompose. But what this means, and what will be true, is that the solid will not decompose into gases, and here's the most important part, at 1 atmosphere each. That delta G is a delta G value considering standard states. The fact that it's not spontaneous means it is not spontaneous to standard states. So if you just put the solid in there, it will not decompose all the way to 1 atmosphere. But it will still decompose. Just not to standard conditions. Now, later on, we will look at, well, what will it do then? But we're not there yet. Okay? Questions? All right. Now we're going to change the temperature. All right, so this next thing is now at 300 degrees Celsius. And so at 300 degrees Celsius, of course, that changes our temperature, and our delta G equals delta H minus T delta S. And so what we get is delta G is now positive 13 kilojoules. What does that mean, positive 13 kilojoules? It's still not spontaneous, right? So that hasn't changed. But certainly the delta G value has changed. All right, so some interpretations of this then. And you're going to feel like I'm repeating myself, and I kind of am going to repeat myself. So, at 300 degrees, if you put the reactants and products all together at standard states, at 25 degrees Celsius, it's still positive, so it's still true that the reverse reaction is going to be favored to equilibrium. I totally mean at 3. Yes, I do. That wouldn't make sense. Thank you. So it's the same idea. Even though the temperature is hotter, we still have that same interpretation. And the same thing is also true if you have just the solid at 300 degrees Celsius. Bless you. The solid is not going to decompose to gases at 1 atmosphere each. Again, doesn't mean it won't decompose. They're just not going to decompose all the way to 1 atmosphere each. All right, now we need to think about the fact that that delta G value actually changed here. And so that positive 13 kilojoules is certainly less than the positive 91 kilojoules that we found. So this is at 300 Kelvin. Versus what we found, not 300 Kelvin, degrees Celsius, versus what we found at 25 degrees Celsius. What does that tell you? What do you think, Rajan?
So as you increase the temperature, the reaction is not that it becomes more spontaneous, but like once you increase, if you kept increasing the temperature, it would eventually become spontaneous.
Yeah, so what we can see is as we're increasing the temperature, it's getting closer to 0, and therefore if you keep getting hotter, perhaps even closer to being negative, so being spontaneous eventually. And that's absolutely right. So, what does that mean? Well, at this point, less energy is required at 300 degrees for the reaction to reach equilibrium. And we will take a look and see, well, what happens? What point do we kind of cross over to start to become negative? So we will look at that. The other thing I want us to take a look at is just kind of in general. I'm going to rewrite the equation down here that we're considering. This reaction was endothermic or exothermic? Endothermic. So that's like energy is a reactant here. What we did is we took the temperature at 25 degrees and then we raised it. We heated it up to 300 degrees. And looking at this reaction, if you heat it up, in which direction does this equilibrium shift? To the right. It shifts to the right. If it shifts to the right, then we're going to be making more products. And so we're more likely to get them to 1 atmosphere each. We're not there yet, but we're making more products. So we're going to be closer to getting them to 1 atmosphere. And so Le Chatelier just kind of confirms that for us. All right, so flip over to the next side. And we'll go ahead and look at that crossover temperature. Like, when are we going to hit the point when it stops being non-spontaneous and starts being spontaneous? So we're going to look at that equation that we know, this delta, G is equal to delta H minus T delta S. Actually, we're doing these with little knots here. The crossover temperature, if you think about yesterday, we talked about the crossover temperature with water boiling, being 100 degrees Celsius for that. That's the equilibrium temperature. At equilibrium, delta G is 0. So if that's true, then we have, 0 is equal to delta H minus T delta S. And what we're going to do is solve for that temperature. So then temperature is going to be equal to delta H over delta S. And we know these values because that's on the front of the page. So our delta H value was 176 kilojoules. And our delta S value in kilojoules was 0.8245 kilojoules per Kelvin. And so when we solve for that, we get 619 Kelvin. Or 346 degrees Celsius. So this kind of confirms, we saw we were getting closer to equilibrium, and so now we keep raising the temperature from 300 to 346, and now at 346 degrees, that's when we reach equilibrium. So, meaning, first of all, this is what we would call the standard state equilibrium temperature. And it also means that if you're at 619 Kelvin and you mix reactants and products at standard states, so you take the ammonium chloride and you take 1 atmosphere of HCl and you take 1 atmosphere of ammonia and you put them all into the same container, it will be at equilibrium. That's the temperature that's at equilibrium. Or at 619 Kelvin, if you have just the solid will decompose to gases at 1 atmosphere each. So it'll decompose until the partial pressures of those gases are 1 atmosphere each, and then it'll be at equilibrium. Okay. Hi, Mr. Jensen. Scared him off. How you doing out there? Maddie.
So like once you get above 619,000, will it start to decompose?
I'm so glad you asked. Let's go ahead and discuss that. So, if you get above 619 Kelvin, it will decompose. Like, let's say you put the solid in a container, it will decompose. What will it decompose to if you're hotter than 619 Kelvin? What do you think? What will the pressures be? Will they be 1 atmosphere? What will it be then? More or less than 1 atmosphere? More. So at 619 Kelvin, it will decompose to 1 atmosphere. Above 619 Kelvin, the solid will decompose to gases that are actually above 1 atmosphere each. Say greater than 1 atmosphere each. And if we think about, and we will compute this in a moment, if we're below 619 Kelvin, which was some of our calculations just a moment ago, the solid will decompose to gases less than 1 atmosphere each. So it'll actually go further. So only at 619 Kelvin will it actually decompose to exactly 1 atmosphere. Okay, before that, like when we were at 25 or 300 degrees, it would decompose, but it wouldn't quite get to 1 atmosphere. At 619 Kelvin, it gets to 1 atmosphere. Above 619 Kelvin, now it's more than 1 atmosphere. Okay? All right, next thing. What about non-standard states? Delta G naught is referring to 1 atmosphere, 1 molar. A lot of times we don't care about that. So let's say here that we have a 10th atmosphere each instead of 1 atmosphere each. All right, this equation that is here, might be on your useless information sheet. I don't know. I haven't looked recently. But what this equation here is, it actually has you solving for delta G. Notice there's no little naught symbol. So this is delta G at non-standard states. And in order to compute it, you need the delta G at standard states. And then this RT natural log Q is an adjustment for being at non-standard states. That's what that really is. It's a way to adjust standard state delta G to non-standard state delta G. Now, Q is the reaction quotient. So if we think about this equation here, the KEQ for this is going to be the partial pressure of ammonia times the partial pressure of hydrogen chloride. We don't put the solid, of course. And so when we talk about Q here, that is the whatever conditions we're at, plugging it into the K expression. So when we look at this delta G, finding delta G when we're at 10th molar instead of 1, or 10th atmosphere instead of 1 atmosphere, we have our 13 kilojoules. That was our delta G naught from the first page. Here's our R. Notice it's not the liters atmospheres version. That's not going to make much sense. It's the 8.314 version. But I've changed it into kilojoules so that the units will work out. That's the only difference. Here's our 300 degrees Celsius in Kelvin. And this natural log 0.10 squared is because if we're at a 10th atmosphere each, then we're at a 10th atmosphere of ammonia and a 10th atmosphere of HCl, and we're going to take the natural log of that value. That's what the adjustment is. So that's where that came from. And notice when we do that, we end up with a delta G that's negative 9 kilojoules. Which tells you what? This is spontaneous. Okay, spontaneous. All right, so let's interpret it. So, at 300 degrees Celsius, if you mix reactants and products at standard states, which reaction will be favored, the forward or the reverse? If it's negative. It's spontaneous, right? So forward or reverse? Forward. So the forward reaction will be favored to equilibrium. Mark. Yes, I do. That's why you got to keep me honest here, people. We're not. See, I keep repeating myself. I just mix reactants and products at 0.1 atmospheres each. How about that? Instead, yeah, you're all over that, right? Good job. So yes, that's what I actually meant. If you put them in the container at a 10th of an atmosphere each, the forward reaction is going to be favored to equilibrium. Think about that, you guys. if you are putting in this equation up here, you know, you have a 10th atmosphere and a 10th atmosphere and the forward reaction is favored, where are you going to end up? Are you still going to be at a 10th atmosphere? No, you're going to be higher than that, right? Until it reaches equilibrium. Or, if you have just the solid at 300 degrees Celsius, it will decompose to what? Is it going to decompose to gases at a 10th of an atmosphere? Would it be more or less? More. It'll decompose to gases that exceed a 10th of an atmosphere. And we'll do some math in a moment so we can see where that comes from. Okay. How you doing? Nobody's sleeping yet. It's good. Awesome. All right. Next page is the last page. We're almost done. Look at that. All right. So we are going back to 25 degrees Celsius, where we started. And what we learned when we started is that at 25 degrees Celsius, it is not going to decompose to gases at 1 atmosphere each because it was non-spontaneous. About positive 91 kilojoules, right? So now the question is, well, if it's not going to decompose to 1 atmosphere each, what is it going to do? So in order to figure that out, remembering that whether it's spontaneous or not spontaneous, it is going to proceed in a way until it hits equilibrium. I mean, at some point it's going to hit equilibrium. So we're going to impose these equilibrium conditions. So at equilibrium, we're not going to assume we're at standard states here because we know it's not going to do that at standard states. At equilibrium, delta G is 0. And at equilibrium, instead of using Q, Q will now become equal to our KEQ. Because it'll be at equilibrium conditions. So, we need a new equation that we're going to derive here. We'll start with the old one. Delta G is equal to delta G naught plus RT natural log Q. But now, based on what we've just imposed, we know that delta G will be 0 and Q will be KEQ, or I'll just call it K. So if that's true, then 0 is equal to delta G naught plus RT natural log K. And delta G naught is equal to negative RT natural log K. This equation is on your useless information sheet. It's a pretty important equation because here's what it tells you. If you know delta G naught, you can figure out the KEQ for the reaction. Or if you know the KEQ for the reaction, you could figure out delta G naught. So you could go in either direction. All right, so we're going to use this equation. We're going to use it to figure some stuff out because we already know the delta G naught. And remember here, we're at 25 degrees Celsius. So that was that positive 91 kilojoules. That's equal to our gas law constant, 0.00831. That's in kilojoules, not joules. Whew, just lost my whole box. Kilojoules per mole Kelvin. The temperature is 25 degrees Celsius, so 298 natural log K. And so K, if we solve for it, is 1.1 times 10 to the minus 16. When the KEQ is that small, what does that tell you about your equilibrium reaction? When KEQ is that small, favors the reverse reaction, right? There's going to be a lot of reactants, but not many products, right? The products would be very, very small. And so this tells us that the reverse reaction is favored Why? Because there are very few products. That's how we end up with a K value that's that small. All right, so we're going to use that then. We know our KEQ is equal to the partial pressure of ammonia times HCl. And now we know that's 1.1 times 10 to the minus 16. And since this reaction, which I'm just rewriting up here again, it's breaking up into a 1-to-1 ratio of ammonia to HCl, then we know that ammonia is going to be equal to the pressure of the HCl. Sort of like x squared equals the K value. And so that's going to be equal to the square root of the KEQ. And when you do that, you end up with 1 times 10 to the minus 8 atmospheres. That helps us to answer the question of what will it do? So I want you to think about this for a moment. If we take a container, and in that container we put 1 atmosphere of HCl and 1 atmosphere of ammonia, and we put some solid ammonium chloride in it, we know, because it was not spontaneous, that the reverse reaction is going to be favored to equilibrium. So looking at this, the reverse reaction is going to be favored to equilibrium, so it's going to start using up the ammonia and the HCl. Well, at equilibrium, what is going to literally be left in the container? What is going to be left in the container? Jordan, what do you think? Okay, I agree. There's some ammonium chloride still left in the container. Are there the gases left in the container? Yeah, how much? 1 times 10 to the minus 8. That's what this tells us. So we have 1 times 10 to the minus 8 atmospheres of HCl left. We have 1 times 10 to the minus 8 atmospheres of ammonia left. So in other words, the HCl and the ammonia get used up until their pressures drop to those values. And then it's at equilibrium. Or if we start with just the solid in a container and no gas, that solid will start to decompose until it reaches pressures of 1 times 10 to the minus 8 for each one of them. That's literally what that means when we get that value. Okay? All right. Let's try it at 300. So back to 300. So we can use that new equation, delta G naught is equal to negative RT natural log K. But now at 300, our delta G was positive 13. It dropped, remember? So we can plug that in. And that's equal to the gas law constant times now 573, because we're at 300 degrees Celsius, natural log K. Knowing that this was endothermic, and knowing that we're heating it up, and so the reaction is going to progress to the right, should our K value be bigger or smaller? Lauren? Bigger. Okay. And in fact, if you do the calculations, you get 0.067, which is quite a bit bigger than the 1.1 times 10 to the minus 16. And the fact that it was endothermic, and we know the delta 8, and we heated it up, tells us that. So this tells us really that at 300, the products are more favored than they were at 25 degrees. Are more favored. Because our K has gotten bigger. So now we're going to be producing more products at this higher temperature than we were. And we could do the same thing. We know that K is going to be equal to ammonia times HCl, and that's going to be equal to 0.067. And it's still a 1-to-1 ratio, so the partial pressure of ammonia is going to be equal to the partial pressure of HCl, that's basically x squared. And so you take the square root, and so what you end up with is 0.26 atmospheres. So that means that at 300 Kelvin in our container, whether we start with gases in there or just the solid, in the end, we're going to end up with 0.26 atmospheres of HCl and 0.26 atmospheres of ammonia. And maybe we did that because we just put the solid in the container and that's it, and it decomposes until it makes this much stuff. Or maybe we put 1 atmosphere of each and the solid in there, and the reverse reaction is going to be favored until it drops to this much. That's what those numbers are indicating to us. Okay. Questions? Okay. Almost done. Full circle. Van't Hoff equation. Please tell me that sounds vaguely familiar to you. Okay, good. Like that one wasn't that old. All right, Van't Hoff equation. Natural log of K2 over K1. This is, one of our 3 that has the same format here. This is the change in enthalpy versus the temperatures. So this was the Van't Hoff, so it relates change in temperatures to how the equilibrium constants change. Well, we've just found the 2 equilibrium constants at 2 different temperatures, so we're going to use that to find delta H. So the natural log of our K2 here, 0.067, divided by the first one, which was 1.1 times 10 to the minus 16th, is equal to delta H naught over our R, 0.00831 kilojoules per Kelvin. And then we had our 2 temperatures, 25 degrees and 300 degrees, but we need those to be in Kelvin. So 298 Kelvin for the 25, 573 Kelvin for the other. And in doing this now, we can actually solve for delta H. And when you do that, you get positive 176 kilojoules. Which is what we started with in the beginning when we said it was endothermic. So here's what we've done. Okay? I took this one reaction and I took you through looking at delta G at 25 degrees and at 300 degrees, and then we changed it from standard conditions to non-standard conditions, and then we used that information to try to find K values, and then we took those K values and confirmed the delta H. What I've done is taken you through the bulk of all the different calculations you may find in the chapter. Your chapter is not going to use the same example all the way through. They're going to use different examples for different things, and that's okay, because now what you're seeing is you're seeing it one way here, and as you do the reading and you work through the blues, you'll get to see other examples of them. But there are some key formulas that I kind of highlighted for you in here that you're going to use. But my goal was today is by taking you through this is that you can get an understanding of, well, if it's not spontaneous, that doesn't mean it's not going to happen. It just means it's not going to happen to the conditions you have set. Maybe those conditions are standard conditions. Or maybe those conditions are 10th atmosphere conditions. Or maybe they're, 0.1 molar conditions. So spontaneity is very specific to the conditions you determine. Will it go to equilibrium at those conditions? Well, okay, yes or no. And that's what we're looking at. Okay. So that finishes today. That's, like 3/4 of the chapter. And what you have right now is you have a little bit of time to maybe look at some of the reading or to look at some of the blues right now. Okay?